Hello and welcome to this video tutorial on the chi-squared statistical test, inferential statistical test that we use in OCR A-level psychology. Okay, the question that I'm going to go through with you is this one. Okay, we're going to use just to demonstrate how to use this particular statistical test. So the question is there a difference in voting preference between the older and the younger voter? Now you might imagine that there probably is, okay, but we're going to look at that by some figures. Okay, so what we've got here is what's known as a contingency table. So you can pretty much work out as soon as you get a contingency table that you're going to be doing a chi-squared analysis. So what do we mean by that? So we've got what's called a 2x2 contingency table. So just to make sure you remember, these are the rows. Okay, rows go across and the columns go down. All right. So we've got left wing and we've got right wing. And we've got young and old. So these are the voting intentions and these are the age groups of the people. All right. And you can see in the contingency table as well, we have these things called cells. Okay, so the cells, first of all, have what we call the observed values. So the observed values are what have actually been generated from the test, from the questionnaire, or whatever it was that was done here. And these cells, okay, we've actually got written down cell A, cell B, cell C, cell D. Sometimes what happens here is you get another figure in here as well, which is known as the expected value. Okay, but more of that later. Okay, just make sure that you have actually labeled them up as cell A, cell B, cell C, and cell D. And for the moment, ignore the red numbers. Right, what we're going to do with this, the first thing it's going to ask you to do is to write a two-tailed alternative hypothesis for the study. Okay, so in this particular case, well, in any case, we always write a null hypothesis and we write an alternative hypothesis. We've been asked to do a two-tailed alternative hypothesis. So the two-tailed hypothesis basically just says that there's going to be a difference, but we don't know which way it's going to go. It could be that the older people are going to vote more right wing, or it could be that they vote more left wing. But whatever it is, it's going to be different to the younger voters. Obviously, if it's a one-tailed hypothesis, we'd have to be more specific than that. So this is how we write it. There will be a statistically significant difference between age over and under 25. You can see how we've operationalized the variable there, and voting preference, left wing versus right wing. Okay, but things don't always work out in psychology. You always have to have a backup plan. So we always have a null hypothesis, which simply states that now there's not going to be a difference, or if there is going to be a difference, it's not going to be due to age. It's going to be some other factor, or just simply a chance occurrence because of this particular study design. Okay, so a null hypothesis is this: there will not be a statistically significant difference between age and voting preference. And we always stick this little bit in at the end here. Any difference will be down to chance alone. Next question asked you, why would you use a chi-squared analysis here? Well, we would use a chi-squared analysis because we have nominal data. That's the first thing to point out. So nominal data is the most simple type of data that you can have. And in this particular case, it is nominal data because if you look at it, we've just got two categories here. You can either be left wing or right wing. That could have been different, couldn't it? That could have been presented in voting preference in terms of Conservative, Labour, Liberal Democrats, UKIP, I don't know, whoever there else is out there, but those are the things that could have been done. But all we've done here is to put it left wing, right wing, and also nominal data here as well. You can either be young or you can be old. You see how those are very, very broad categories, and you can only belong to one or the other. So that's why it's nominal data. The other reason why it's a chi-squared test is we're looking for a difference here between the two variables, and we've also got an independent measures design. Why is it independent measures? Well, you can't be young and old at the same time. So what that will necessarily mean is that there are different people in different categories. Okay, so that means you have an independent measure design. Okay, right, let's start working on this table then, because we need to work out what chi-squared is. And the first thing we do is we add up the totals for the columns, and then we add up the totals for the rows. Okay, so we get these total things, and then we end up with a grand total at the end. Okay, so columns, 5 plus 12 equals 17, 10 plus 9 equals 19, 5 plus 10 equals 15, 12 plus 9 equals 21. Okay, add them all up, we get 36 there. Hopefully that makes sense. That's the first thing. Without doing that, we are going to struggle to do the rest. Right, okay, that looks a little bit frightening at the moment. Don't be frightened by it, because if you remember, all we do with statistical tests is that we break them down into the simple steps, okay? And as we go through the steps, we do it systematically, we end up with the right results. So that is the chi-squared formula, and it basically tells you that you've got to go through those steps, doesn't it? Right, let's see what we need to do next, and this is the fiddly bit. Okay, so what I've done is I've just copied over that table from above so you can see where I'm going to get these results. All right. So first thing, cell A, B, C, D down the side, and these are the 4 different columns that you need. Stop that blinking there. Be useful, wouldn't it? Okay, there we go. So we have row times column divided by total will give us our expected frequency. So the expected frequency is for each cell what we would have expected to get, right? We do that by simply timesing the row by the column and dividing it by the total, and doing that for each cell. So let's just work through a few. Okay, so for the first one, for cell A, 17 is our row, 15 is our column, and then 36 is our grand total. So it's going to be 17 times 5 divided by 36, 7.08. Can you all see that? Yeah. Let's go to another one. Let's go to cell D, just to truncate this a little bit for you. Cell D, we've got the row total is 19. There you go, 19. Yeah. Times 21. Times 21 divided by 36. Yep, and that equals 11.08. Now we've got our expected frequencies, we're good to go. That is the most fiddly part of it. We're going to go E minus O in this particular case. I could have gone O minus E. It doesn't make any difference really. It's just going to get a figure, a difference between the observed and the expected value. 5 minus 7.08, we'll just ignore the minuses. It doesn't make any difference. 2.08. 12 minus 9.92, 2.08. Again, you can see we get the same figure the whole way down there. Okay, do that for each of the cells. We're going to square the previous value. Okay, so we get those figures there. Okay. And the last one, we divide the previous value by the expected value. So E minus O squared divided by E. Okay, so in this particular case, we get 0.6110, 0.4361, 0.5463, and 1.3905. Okay, hopefully that makes sense. So that's that bit there divided by the expected value for each cell. So that's going to be 4.3264 divided by 7.08 for that one. Okay, that'll give you 0.611. Oh, hopefully that makes sense for you. Right, we add them all up. That gives you your grand total, and chi-squared equals 1.984. So we have what's known as an observed value here, an overall observed value of chi-squared, which is 1.984. All we now need to do in order to work this out, just a couple of steps. We need to work out what's called our degrees of freedom. So we don't have n numbers on chi-squared. That would be far too easy. We have degrees of freedom. And the way we do that is simply by multiplying the number of rows minus 1 by the number of columns minus 1. So in this particular case, because we've got a 2 by 2 contingency table, we have 2 rows, 2 columns, 2 minus 1 times 2 minus 1 equals 1. So the degrees of freedom will equal 1. Right. On to, honestly, this is almost at an end here. Degrees of freedom, this is the critical value table. So we're going to use our critical value table to work out whether we have a significant result. Chi-squared equals 1.984. Yep. We have a two-tailed test, and we have a degrees of freedom of 1. What's our critical value? 3.84. With a chi-squared test, our observed value of chi-squared must be equal to or greater than the critical value in the table for significance to be shown. 3.84 is our critical value, 1.94 is our chi-squared. Unfortunately, after all that, we do not have a significant result because chi-squared, our observed value of chi-squared, is less than the critical value in the table. Oh dear, right then, so what does that mean? Next question says, can you accept the alternative hypothesis? Sadly, no. The observed value 1.984 is less than the critical value at DF equals 1. That's 3.84 in that particular case, wasn't it? Is therefore not significant. Hopefully you can see that. Here's our significant statement. chi-squared 1.984, df equals 1. The probability is greater than 0.05, so that's another way of showing a non-significant result. Okay, hopefully that's helped. You might need to go through this video more than once in order to see how this works. But yeah, any questions, obviously you know where we are. Many thanks.